everyone. In this video, I'd like to talk about an object that is falling down towards Earth. So in this model, I'm going to assume that the upwards direction away from Earth, that refers to positive velocity, and that downwards motion has negative velocity. So that's just how I'm defining my coordinate system. And so if I look at the differential equation model, I've got mass times dv dt equals negative m times g, so that's the acceleration due to gravity on Earth, minus k, which is some constant, times v, velocity. So basically, I've got two forces here. I've got the gravitational force that's pulling my object down towards Earth. And then I've got some resistance, which is really modeled by this parameter K. And so this could be air resistance, or it could be, if you're falling through some sort of thick liquid like oil or water or something, you're going to have a different sort of K parameter there. And similarly, if you're jumping out of a helicopter with a parachute, your K value is going to be very different than if you jump out of the helicopter with just your own body, which is probably a good thing and why they invented parachutes. But to get on with the model and take a look at how this works, I'm going to assume, and these are just the pretend values for my problem here, I'm going to assume that M equals 10 grams and that K equals 2. So if I plug those values into my differential equation, I'm going to get 10 times dv dt equals negative 10 times 9.8, and I'll leave out the meters per second squared just to keep everything clean, minus k, which I know is 2, so let's put that in there, times v, which is velocity, and we don't know what that is right now. Our goal in solving this differential equation is to figure out what is v and come up with some sort of equation for velocity and maybe talk about the terminal velocity of this person that has jumped out of the helicopter. So I'm going to clean this up a little bit. I'm going to divide everybody through here by 10. And on the left-hand side, I'm left with dv dt. And on the right-hand side, in my first term, I have just a negative 9.8 because those 10's canceled. And then in the second term here, I still have a negative 2 over 10. So I'll just write that there, times velocity. So the first task is to create a slope field. And then I'll come back here to the blackboard and we'll actually solve the differential equation. So I'm over here in GeoGebra and I have typed in the differential equation into this little box right here, and notice that they're using y's and x's instead of v's and t's. We won't be bothered by that. That's okay. But I do have the correct equation in there, and you can set any sort of mins and maxes that you want. And I wanted to be sure to show this kind of trending off behavior down here. So I do really want to be looking at all four quadrants just to make sure I see the full picture of what's going on, and I do. So that's my slope field. So what this is a picture of, this is a picture at every little XY point, or if you want to think about different variables like v and t, at every little point, you've got an idea of what the slope looks like. So now let's come back here and actually solve this differential equation. This is what's known as a separable differential equation. So this is a separable differential equation, and that's one of the nicest types of differential equations to encounter because you can just separate the variables and then integrate both sides, and we're kind of back to Calc 1 or Calc 2 sorts of maneuvers. So my first task is to separate the v's and separate the t's. So the first thing I'm going to do here is I'm going to rewrite this as dv on the left, and on the right hand side I'm going to write this as negative 9.8 minus, well, let's call it a 0.2 instead of the fraction there, v dt. Now, on that right-hand side, I've got a mixture of v's and t's. So let's, again, goal is to separate. So I'm going to divide both sides by negative 9.8 minus 0.2v. I'm going to do that on both sides. And of course, I'm out of room, but you can see what I'm doing there. Okay. On the left-hand side, I have 1 over negative 9.8 minus 0.2v dv. And on the right-hand side, I just have 1 dt. Now, we're ready to just integrate both sides. So I'm just going to integrate the left, and I'm going to integrate the right. So let's make a little bit of space here. I'll come on over to the side here. So integrating this, I've got the integral of 1 over negative 9.8 minus 0.2v dv, and that's going to require a u substitution. So I've got u equals negative 9.8 minus 0.2v. Differentiating, I get du dv equals negative 0.2. Well, what does that tell us? That tells us that du equals negative 0.2 dv. And although I do have a dv in my problem, oops, I made a typo right here, let me correct that. Although I do have a dv in my problem here, that looks good, I don't have a negative 0.2 dv. So I better get rid of that so that I can make a nice substitution. So on the left-hand side, I have 1 over negative 0.2. We could call that negative 5. Du equals dv. And that's lovely. That is really good because now I know what to substitute in for dv. So let's do that. I've got the integral. Instead of 1 over this complicated expression, now it's just 1 over u. And instead of the dv, I know that my substitution for dv is going to be negative 5. I'll put that in front, du. Integrating, I have negative 5 times the natural log, the absolute value of u, and going back to the language of v's, that'll give me negative 5 natural log of negative 9.8 minus 0.2v. So my left-hand side looks great. I'm done over there. I've got a negative 5 natural log absolute value, negative 9.8 minus 0.2v. And then on the right-hand side here, the integral of 1 dt, that's just t, and you could put a constant on the whole thing there. From here, your next step would be to solve for v, and if you're a student of mine, I'll work that out in the course. But I do want to show you, once you solve that for v, and you can do that even in Wolfram Alpha and verify you get the correct solution. But once you solve for v, then you can hop over here and you can add your solution onto the slope field. So again, what this shows us is that for different initial conditions, so here's an initial condition close to 0. When time equals 0, if our velocity is 0, that's the curve we would get. That's this particular solution we would get, in fact. And then, if we had a different initial condition like over here, we'd get a different particular solution to the differential equation. So you can kind of look at the different types of particular solutions you'd get given different initial values that you start with.